Teleportation is officially real. Star Trek is here. In November 2025, scientists achieved something that seemed impossible. They teleported quantum information between photons that had never met, had never shared a source, came from completely different origins. Star Trek's transporter is still science fiction, but quantum teleportation, that's becoming science fact. Welcome to Sleep Entangled, where quantum breakthroughs and wonder merge into late-night explorations. If you find fascination in these journeys to the edges of the possible, remember to subscribe and let curiosity guide your nights. Now, relax, breathe deeply, and let's explore how teleportation moved from Star Trek to Stuttgart. Chapter 1. The Dream of Teleportation. Beam me up, Scotty. 4 words that captured humanity's imagination. Captain Kirk, standing on an alien world, tapping his communicator, dissolving into shimmering light, and reappearing safely aboard the Enterprise. Instantaneous travel across impossible distances, matter transformed into energy, transmitted and reconstructed atom by atom. Pure science fiction, of course. Or is it? For most of the 20th century, teleportation seemed to violate the fundamental laws of physics. To teleport an object, a person, a book, even a single atom, you'd need to scan it perfectly, recording the position and state of every particle. Then you'd transmit that information and use it to reconstruct an exact copy at the destination. But quantum mechanics says this is impossible. The Heisenberg uncertainty principle forbids measuring both the position and momentum of a particle with perfect precision. And the no-cloning theorem, proven in 1982, states you cannot make a perfect copy of an unknown quantum state. So teleportation, it seemed, was fantasy. A dream confined to television screens and science fiction novels until 1993. In that year, a team of 6 physicists, Charles Bennett, Gilles Brassard, Claude Crépeau, Richard Josza, Asher Perez, and William Wouters, published a paper titled Teleporting an Unknown Quantum State via Dual Classical and Einstein-Podolsky-Rosen channels. The title was dense, technical, almost impenetrable, but the content was revolutionary. They proved, theoretically, that quantum teleportation is possible. Not the teleportation of matter, but of information, specifically the quantum state of a particle. You couldn't teleport a person, but you could teleport the quantum information describing a photon, transferring it to another photon light years away, without the information ever traversing the space between. The trick involves quantum entanglement, Einstein's spooky action at a distance. By entangling 2 particles and performing clever measurements, you can destroy the quantum state at one location and recreate it at another, perfectly, instantly. The original state is destroyed in the process. You're not copying, you're transferring. And crucially, you never violate the uncertainty principle or the no-cloning theorem. The quantum information moves, but you never know what it is. In 1997, just 4 years after the theoretical proposal, Anton Zeilinger's team at the University of Innsbruck performed the first experimental quantum teleportation. They teleported the quantum state of a photon across a distance of several meters. It was a milestone, proof that teleportation was real. But the photons used were entangled through a shared source, created together in a process that linked their fates from birth. This dependency limited applications. Real-world quantum networks would need teleportation between particles that had never met, and that brings us to November 2025. On November 14th, a team at the University of Stuttgart, led by physicist Harold Weinfurter, announced a world-first achievement. They teleported quantum information between photons with no common origin. The photons came from independent sources, had never interacted, and yet teleportation succeeded. This breakthrough removes one of the last barriers to building practical quantum networks, systems that could enable ultra-secure communication, distributed quantum computing, and perhaps one day, a quantum internet linking labs and cities across the globe. But to understand why this matters, we must first understand what quantum teleportation actually is. How does it work? What's being teleported? And why is it so powerful? Let's begin with the basics, gently unpacking one of the strangest and most elegant phenomena in all of physics. Imagine you have a photon, a particle of light, in an unknown quantum state. Perhaps it's polarized vertically or horizontally or in some superposition of both. You don't know. Measuring it would collapse the superposition, destroying the information you want to preserve. Your goal is to transfer this state to another photon, far away, without physically sending the first photon and without measuring its state. Classically, this is impossible. You can't transmit something you don't know, but quantum mechanics offers a loophole: entanglement. You prepare two photons, call them B and C, in an entangled state. Photon B stays with you. Photon C is sent to a distant location, perhaps across a city or across the galaxy. Now, you perform a special type of measurement called a Bell state measurement on your original photon, A, the one whose state you want to teleport, and photon B, your half of the entangled pair. This measurement doesn't tell you the state of photon A. Instead, it tells you something about the relationship between A and B, how they're correlated. The measurement outcome is random, falling into one of four possible categories. Here's the magic. The moment you perform this measurement, photon C, the distant half of the entangled pair, instantly acquires information about photon A's state. Not the complete state, but a scrambled version of it. You then send your measurement result. A simple classical message, 2 bits of information to the distant location. Using this information, the recipient can apply a correction to photon C, transforming it into an exact replica of photon A's original state. Photon A is destroyed in the measurement. Photon C becomes A. The quantum state has teleported. No information travelled faster than light. The classical message, the measurement result, travelled at normal speeds, perhaps via fibre optic cable or radio. But the quantum correlation, the entanglement, allowed the state to be reconstructed without ever existing in the space between. This is quantum teleportation. Not the movement of matter, but the transfer of quantum information, using entanglement as a resource. It sounds like magic, but it's physics. Beautiful, bizarre, and since 1997, experimentally verified thousands of times. Yet until November 2025, one limitation persisted. The entangled photons always came from a common source. They were siblings, born together in a non-linear crystal or parametric down-conversion process, sharing a quantum heritage. The Stuttgart breakthrough changed that. Weinfurter's team teleported states between photons from independent sources, strangers, not siblings. This proves that teleportation can work in real-world quantum networks, where nodes might be built by different manufacturers, operate independently and have no shared history. As you settle into stillness tonight, let this image form. 2 photons, born in different laboratories, having never met, separated by distance and time. Yet through the strange mathematics of quantum mechanics, one can inherit the state of another perfectly, without the information ever crossing the gap. This is not science fiction. This is November 2025. This is real. In the next chapter, we'll explore the physics in detail, how entanglement enables teleportation, and why the process doesn't violate relativity or causality. Chapter 2. The Physics of Impossibility, How Teleportation Works. Let's slow down and truly understand the mechanism. Quantum teleportation is subtle, and the subtlety is where the beauty lies. We begin with 3 photons: Alice, Bob, and Charlie. Physicists often personify particles. It makes the explanations warmer, more human. Alice holds photon A, whose quantum state she wants to teleport. Bob and Charlie are entangled photons, created together and sharing a quantum bond. Bob stays with Alice. Charlie travels to a distant location, held by, let's call her, Eve. Photon A is in some unknown state. We can represent it mathematically as alpha vertical H plus beta vertical V, where vertical H and vertical V represent horizontal and vertical polarization, and alpha and beta are complex numbers encoding the state's properties. Alice doesn't know alpha and beta. If she measures photon A, the state collapses and the information is lost. So instead, she performs a Bell state measurement on photons A and B together. A Bell state measurement is a joint measurement that doesn't reveal the individual states of A or B, but rather reveals how they're correlated. There are 4 possible outcomes, corresponding to 4 entangled states, the Bell states. When Alice performs this measurement, something remarkable happens. Photon A's state is destroyed, absorbed into the measurement apparatus, collapsed, gone. But at the same moment, photon C, far away, undergoes a transformation. Its state becomes related to A's original state in a specific way, determined by Alice's measurement outcome. However, photon C's state isn't quite identical to A's original state. Not yet. It's a scrambled version. Depending on which of the 4 Bell states Alice measured, photon C's state might be rotated, flipped, or otherwise transformed. Alice now sends her measurement result, 2 classical bits of information, to Eve. This message travels via normal communication channels, respecting the speed of light. Eve receives the message and knows which transformation photon C underwent. She applies a corresponding correction, a quantum gate that undoes the transformation. If Alice measured Bell state 1, Eve applies operation 1. If Alice measured Bell state 2, Eve applies operation 2, and so on. After Eve applies the correction, photon C's state is identical to photon A's original state. The teleportation is complete. Let's pause and appreciate what happened. Photon A's state was unknown. It was never measured. It was destroyed at Alice's location and recreated at Eve's location, without the state ever existing in the space between. The only information transmitted classically was 2 bits indicating which correction to apply. A message that contains no information about the original state itself. This is the essence of quantum teleportation. Entanglement provides a quantum channel. Classical communication provides control information, and together they enable state transfer that would be impossible classically. But here's a crucial point. This doesn't violate relativity. Information does not travel faster than light. Why? Because Eve cannot extract any information from photon C until she receives Alice's classical message. Before that, photon C is in a mixed state, a statistical blend of all 4 possible transformations, completely random, containing no information. Only after Eve receives Alice's message and applies the correction does photon C's state become meaningful. And since Alice's message travels at light speed or slower, causality is preserved. Similarly, this doesn't allow faster than light communication. Alice cannot choose which Bell state she measures. The outcome is random, determined by quantum mechanics. Eve receives a random transformation of the state, and she can't learn anything from it without Alice's message. Quantum teleportation is often misunderstood. It's not instantaneous travel. It's not cloning. It's not sending matter. It's the transfer of quantum information, enabled by pre-shared entanglement and classical communication. But just transferring quantum information is profoundly powerful. Consider a quantum computer distributed across multiple locations. Qubits need to interact to become entangled to perform computations. But moving physical qubits is difficult. They are fragile, prone to decoherence. Quantum teleportation allows you to move quantum states without moving the qubits themselves. You teleport states between nodes of the network, enabling distributed quantum computing without the risks of physical transport. Or consider secure communication. Quantum states can encode information in ways that are impossible to intercept without detection. Teleportation enables quantum communication protocols like quantum key distribution, which are provably secure against any eavesdropper, even one with a quantum computer. The applications are vast and we'll explore them in later chapters. For now, let's appreciate the elegance of the theory. Quantum teleportation was predicted in 1993, experimentally demonstrated in 1997, and has since been performed across laboratories, cities, and even between Earth and satellites in orbit. In 2017, Chinese researchers teleported the state of a photon from the ground to a satellite 1,400 kilometers above the Earth, using entanglement distributed through space. But all these demonstrations shared a limitation. The entangled photons, Bob and Charlie in our example, came from the same source. They were created together in a process like spontaneous parametric down conversion, where a high-energy photon splits into two lower-energy photons that are quantum mechanically linked. This shared origin simplifies the experiment but limits practical applications. Real quantum networks will have independent nodes, each with its own photon sources. If teleportation only works between photons from the same source, you'd need a central facility generating entangled pairs and distributing them to all nodes, a logistical nightmare that doesn't scale. The Stuttgart team's November 2025 breakthrough solved this. They entangled photons from independent sources using a technique called entanglement swapping, and then used those photons for teleportation. This is a game changer. It means quantum networks can be modular, with nodes operating independently, entangling on demand. It's the difference between a prototype and a practical system. As you rest, imagine the mathematical structure underlying this. Hilbert spaces of infinite dimension, tensor products describing composite systems, unitary transformations representing quantum gates. And within this abstract machinery, a simple, profound result. Information can be transferred without transmission, states can move without matter moving, and the impossible becomes routine. Quantum teleportation is real, and in November 2025, it became practical. In the next chapter, we'll dive into the history, how teleportation went from theoretical curiosity to experimental reality, and the brilliant minds who made it happen. Chapter 3. The Pioneers, from Theory to Triumph. Every great discovery has a story, and quantum teleportation's story is filled with insights, skepticism, breakthroughs, and, ultimately, vindication. It begins in 1935 with Albert Einstein. Einstein was uncomfortable with quantum mechanics. He accepted that it worked. The predictions matched experiments beautifully, but he believed it was incomplete, a statistical approximation of some deeper, deterministic reality. In 1935, Einstein, along with Boris Podolsky and Nathan Rosen, published a paper titled "Can Quantum Mechanical Description of Physical Reality be Considered Complete?" This paper presented what became known as the EPR paradox. The EPR argument involved entangled particles. Measure one, and you instantly know the state of the other, even if they're light years apart. Einstein found this deeply troubling. How could measurement here affect a particle there, instantaneously? He called it spooky action at a distance, and argued that quantum mechanics must be missing something. Hidden variables that determine outcomes in advance, making the correlations only apparently instantaneous. For decades, the EPR paradox remained a philosophical puzzle. Then, in 1964, physicist John Bell proved a theorem showing that any hidden variable theory must satisfy certain inequalities. Quantum mechanics violates those inequalities. Experiments, beginning in the 1970s and perfected by Alain Aspect in the 1980s, confirmed that quantum mechanics was right and Einstein was wrong. Entanglement is real. The correlations are genuine, not the result of pre-shared information. But entanglement was still strange, poorly understood, and, many thought, useless for practical applications. After all, you couldn't use it to send information faster than light. What good was it? Then came Charles Bennett. Bennett, a researcher at IBM, was exploring the foundations of quantum information theory in the early 1990s. He was fascinated by the interplay between quantum mechanics and information, how quantum states could be used to encode, transmit, and process data in ways impossible classically. In 1993, Bennett assembled a team: Gilles Brassard from the University of Montreal, Claude Crépeau, Richard Josse, Asher Perez, and William Wouters. Together, they worked out the mathematics of quantum teleportation. Their insight was that entanglement, combined with classical communication, could transfer quantum states without transmitting them. It was counterintuitive, elegant, and, crucially, respected the no-cloning theorem and the limits of quantum measurement. They published their result, and it stunned the physics community. Teleportation was possible, at least in theory. But could it be done in practice? Enter Anton Zeilinger. Zeilinger, an Austrian physicist working at the University of Innsbruck, was a master of quantum optics, the art of manipulating individual photons with exquisite precision. He read Bennett's paper and immediately saw how to implement it experimentally. In 1997, Zeilinger's team reported the first successful quantum teleportation. They used parametric down conversion to create entangled photon pairs, performed Bell state measurements, and teleported the polarization state of a photon across several meters. It worked. The theory was validated. Teleportation was real. Zeilinger's work earned him the 2022 Nobel Prize in Physics, shared with Alain Aspect and John Clauser for their contributions to quantum information science. Following Zeilinger's success, teleportation experiments proliferated. Teams around the world teleported states across longer distances using different types of particles, photons, atoms, ions, and refining the techniques. In 2004, researchers at the University of Vienna and the Austrian Academy of Sciences teleported quantum states across the Danube River, a distance of 600 meters, using fiber optics. In 2012, Chinese researchers led by Jianwei Pan teleported states across 143 kilometers using a free space optical link. In 2017, Pan's team achieved the ultimate demonstration: teleportation from Earth to the Mikyus satellite, orbiting at an altitude of 1,400 kilometers. They entangled photons on the ground, sent one to the satellite, and successfully teleported states across the vastness of space. These were triumphs, proving that teleportation could work over real-world distances through the atmosphere in practical conditions. But a challenge remained. All these experiments relied on photons from a common source. The entangled pairs were created together, sharing a quantum birthplace. This worked for demonstrations, but real quantum networks would need teleportation between independent sources. This is where Harold Weinfurter and his team at the University of Stuttgart enter the story. Weinfurter, like Zeilinger, is a quantum optics virtuoso. For years, he and his colleagues worked on techniques for entangling photons from independent sources, a process called entanglement swapping. Entanglement swapping is like teleportation's cousin. You start with two pairs of entangled photons, AB and CD, created independently. You perform a Bell state measurement on B and C. This entangles A and D, even though they never interacted, never came from the same source, never met. Once you have entanglement between independent photons, you can use them for teleportation, and that's exactly what the Stuttgart team did in November 2025. They built a system with two independent photon sources, each producing entangled pairs. Using entanglement swapping, they linked photons from the two sources. Then they performed quantum teleportation, transferring the state of a photon from one source to a photon from the other. The teleportation succeeded. The fidelity, a measure of how accurately the state was transferred, exceeded the classical limit, proving that genuine quantum teleportation had occurred. This was the world first, teleportation between photons with no common origin. Harold Weinfurter, announcing the results, stated, "This demonstrates that quantum teleportation can work in realistic network scenarios where nodes operate independently. It's a crucial step toward building scalable quantum networks." The achievement built on decades of work, from Einstein's philosophical discomfort to Bennett's theoretical breakthrough, to Zeilinger's experimental mastery, to Weinfurter's engineering triumph. Each step necessary, each contributor essential. And now, as you drift into rest, imagine this lineage of minds. Einstein in 1935, wondering if reality could be so strange. Bennett in 1993, proving that strangeness could be useful. Zeilinger in 1997, showing it worked. And Weinfurter in 2025, making it practical. Science is a relay race, each generation passing the baton, building on the insights of those who came before. The November 2025 breakthrough is not the end of the race. It's a new lap, opening pathways we've only begun to explore. In the next chapter, we'll examine the November 2025 Stuttgart experiment in detail, the apparatus, the technique, the challenges overcome, and the results achieved. Chapter 4: The Stuttgart Breakthrough. Independent Sources, Perfect Transfer. Let us now descend into the technical heart of the November 2025 achievement. For those willing to journey deeper, the details reveal just how clever the Stuttgart team's approach was. The challenge was straightforward to state, fiendishly difficult to implement. Teleport a quantum state between photons from completely independent sources. Why is this hard? When entangled photons come from the same source, born together in a nonlinear crystal, they're naturally synchronized. Their frequencies, timing, polarization properties, all matched. This makes interference and measurement easier. But photons from independent sources are strangers. They might have slightly different frequencies, arrive at slightly different times, have different spatial modes. Making them interfere, which is necessary for Bell state measurements, is like tuning two violins played in different rooms to produce a single harmonious note. Possible, but delicate. The Stuttgart team, led by Harold Weinfurter, and including researchers Christoph Becker and Tim van Lient, tackled this with meticulous engineering. They built two independent photon sources, each based on quantum dots, tiny semiconductor structures that emit single photons on demand. Quantum dots are attractive for quantum networks because they're solid-state devices, compatible with existing technology, and they can be precisely controlled with laser pulses. Each quantum dot, when excited by a laser, emits a pair of entangled photons. These photons are created through a process called B-exciton cascade, where the quantum dot's electrons transition between energy levels, releasing two photons that are entangled in polarization. The two quantum dot sources were separated, operating independently, with no physical connection or shared infrastructure. This mimics a real-world scenario where quantum network nodes are built by different entities, perhaps in different cities. Step 1 was to generate entanglement between photons from the two sources. This required entanglement swapping. Here's how it works. Source 1 produces an entangled pair, photons A and B. Source 2 produces an entangled pair, photons C and D. Initially, AB are entangled and CD are entangled, but A and D have no connection. Photons B and C are brought together and subjected to a Bell state measurement. This measurement projects them into an entangled state, and, crucially, it entangles A and D, even though A and D have never met. Why does this work? Because the Bell state measurement on B and C correlates their quantum states, and since B was entangled with A and C was entangled with D, the correlation propagates, linking A and D. It's as if two pairs of twins each have a telepathic bond. If you force one twin from each pair into a shared state, the remaining twins who've never met suddenly become connected. Performing this Bell state measurement on photons from independent sources required extraordinary precision. The photons had to arrive at the beam splitter, the device where interference occurs, at exactly the same time, within a window of a few picoseconds, trillionths of a second. If they arrived too early or too late, interference wouldn't happen, and the measurement would fail. The Stuttgart team used fast electronics and feedback systems to synchronize the photon arrivals dynamically. They measured the timing differences between photons and adjusted delays on the fly, ensuring that when photons reached the beam splitter, they were indistinguishable in time and frequency. This level of control is staggering. Photons travel at the speed of light, 300 million meters per second. A picosecond is the time light takes to travel 0.3 millimeters. Synchronizing to picosecond precision is like coordinating two runners to arrive at a finish line separated by the thickness of 3 human hairs, while both are sprinting at light speed. But the Stuttgart team achieved it. Once A and D were entangled via swapping, the next step was teleportation. They prepared photon A in a specific quantum state, a known superposition of polarizations, and performed a Bell state measurement on A and photon E, one half of a new entangled pair from source 1. This destroyed A and scrambled its state into photon D from source 2. Using the classical measurement result, they applied a correction to D, recreating A's original state. To verify success, they measured photon D's polarization and compared it to A's original state. The fidelity, the overlap between the teleported state and the original, was reported at over 85%, well above the 66.7% classical limit. Fidelity above 66.7% proves that genuine quantum teleportation occurred. Classical strategies, trying to guess or approximate the state, cannot exceed 66.7% accuracy. Quantum teleportation, leveraging entanglement, surpasses this limit. The Stuttgart result was a world first, not because they achieved the highest fidelity. Zeilinger's team had achieved 90% plus fidelity in earlier experiments with common source photons, but because they did it with independent sources. This distinction is crucial. It means that quantum networks don't need centralized entanglement sources. Each node can operate independently, generate its own photons, and use swapping to entangle with other nodes on demand. Harold Weinfurter, discussing the implications, noted, "This paves the way for modular quantum networks, where you can plug in new nodes and they'll work together seamlessly. It's like the internet. You don't need a central hub distributing connections. Nodes communicate peer-to-peer." The November 2025 results were published in Nature Photonics, a prestigious journal for optical physics. The paper detailed not just the successful teleportation, but also the challenges overcome: timing jitter, photon loss, detector noise, and the innovations that made success possible. Reviewers praised the work as a milestone in quantum networking and a demonstration that moves teleportation from laboratory curiosity to practical tool. But challenges remain. The current system operates at low rates, a few successful teleportation events per minute. Scaling to thousands or millions per second will require further improvements in photon sources, detectors, and synchronization systems. Additionally, quantum dots, while promising, are still being optimized. They need to be cooled to cryogenic temperatures, they have limited emission rates, and they suffer from spectral diffusion, random shifts in photon frequency that complicate interference. Alternative approaches, using trapped ions or color centers in diamond, are also being explored. The quantum networking field is diverse, with many competing technologies, but the Stuttgart breakthrough proves the concept. Independent source teleportation works. The path forward is clear. As you settle deeper into stillness, picture the apparatus: lasers, fiber optics, beam splitters, detectors, all arranged on optical tables in a darkened lab. Photons zipping through the system, entangled across space, measured, destroyed, recreated. Quantum information flowing, invisibly, carried by light. This is the cutting edge of physics, where theory meets practice, where the impossible becomes routine, where the future is being built, one photon at a time. In the next chapter, we'll explore the broader landscape of quantum networks, what they are, why we need them, and how teleportation fits into the vision of a quantum internet. If you're still with me on this late-night voyage through quantum teleportation, you're part of something special, a community exploring the frontiers where science fiction becomes science fact. A quick subscribe helps others discover how physicists are making Star Trek real. Now, let's continue into the quantum internet, the network that will connect our future. Chapter 5. The Quantum Internet, Networks of Entanglement. Imagine a network where messages cannot be intercepted, where eavesdropping is physically impossible, where security is guaranteed not by clever algorithms but by the laws of nature. This is the promise of the quantum internet. The internet we use today, email, web browsing, streaming, relies on classical communication. Bits of information, encoded as electrical signals or pulses of light, travel through cables and air, reaching their destination in milliseconds. But classical communication has vulnerabilities. Messages can be copied, intercepted, analyzed. Encryption provides security, but it's not absolute. Sufficiently powerful computers, especially quantum computers, could break many current encryption schemes. the quantum internet offers something fundamentally different: communication based on quantum states, transmitted via entanglement and teleportation. A quantum internet wouldn't replace the classical internet. It would augment it, providing specialized capabilities, ultra-secure communication, distributed quantum computing, and networked quantum sensors. Let's explore these applications. Quantum key distribution, QKD. The most mature application of quantum networks is QKD, a method for generating shared secret keys between two parties, Alice and Bob, in a way that detects any eavesdropping. Here's how it works. Alice and Bob share entangled photons. Alice measures her photons in random bases, e.g. horizontal/vertical or diagonal/antidiagonal. Bob does the same. After measurement, they publicly compare which bases they used, but not the results. For cases where they use the same basis, their results are perfectly correlated due to entanglement. These correlated results become their shared secret key. If an eavesdropper, Eve, tries to intercept and measure the photons, she disturbs the entanglement, introducing errors. Alice and Bob detect these errors and know their communication was compromised. QKD has been demonstrated over hundreds of kilometers using fiber optics and thousands of kilometers via satellite links. Companies like ID Quantique and Toshiba sell commercial QKD systems, but current QKD systems have limitations. They require trusted nodes, intermediate stations that regenerate the quantum states, but which must be physically secure. A quantum internet with teleportation and entanglement swapping can eliminate trusted nodes, creating end-to-end security. Distributed quantum computing. Quantum computers are powerful but limited by the number of qubits they contain. What if you could link multiple quantum computers into a network, allowing them to share entanglement and perform joint computations? This is distributed quantum computing enabled by teleportation. Imagine a quantum computer in New York and another in London. Each has 1,000 qubits. Alone, they can tackle certain problems, but connected via quantum teleportation, they can operate as a single 2,000 qubit system, exponentially increasing their power. Teleportation allows qubits in New York to become entangled with qubits in London without physically moving them. Quantum gates can be performed across the network. The computers function as one despite the distance. This could accelerate drug discovery, materials design, and optimization problems beyond what isolated quantum computers can achieve. Quantum sensing and metrology. Quantum entanglement can enhance the precision of measurements. Networks of entangled sensors, atomic clocks, gravitational wave detectors, magnetic field sensors can achieve sensitivities impossible with classical devices. For example, a network of entangled atomic clocks could synchronize time with femtosecond precision, enabling GPS systems with centimeter accuracy, tests of relativity with unprecedented precision, and detection of gravitational waves too subtle for current observatories. Teleportation plays a role by distributing entanglement across the network without disturbing the delicate quantum states being measured. The architecture of a quantum internet. Building a quantum internet requires several components. 1. Quantum nodes. Devices that generate, store, and manipulate qubits. These could be quantum computers, quantum memories, or photon sources. 2. Quantum channels. Fiber optic cables or free space optical links that transmit photons without excessive loss. 3. Quantum repeaters. Devices that extend the range of entanglement by performing entanglement, swapping at intermediate locations, counteracting photon loss. 4. Classical control. Computers that coordinate the network, perform error correction, and route quantum information. Photons are ideal for transmitting quantum information. They travel at light speed, interact weakly with their environment, and can be sent through fiber optics or free space. But photons have a problem. They get absorbed. Even the best fiber optics lose about 0.2 decibels per kilometre. After 100 kilometres, only 1% of photons remain. After 500 kilometres, it's a tiny fraction. For a global quantum internet, we need quantum repeaters, devices that regenerate entanglement without measuring the quantum states. Classical repeaters, used in today's internet, measure the signal and retransmit it. But measurement destroys quantum information. Quantum repeaters use entanglement swapping to extend the entanglement without collapsing the states. Here's the concept. Divide a long distance into segments. Create entanglement between nodes AB, BC, CD. Use entanglement swapping at B and C to link A and D without B or C learning the quantum states. Quantum repeaters are challenging to build. They require quantum memories, devices that store quantum states reliably, and high-fidelity Bell state measurements, but progress is rapid. Several research groups have demonstrated elements of quantum repeaters, and fully functional devices are expected within the decade. The quantum internet timeline. Where are we now, and where are we headed? 2025, current state. Quantum key distribution operational over hundreds of kilometers. Satellite-based QKD demonstrated between continents. Small-scale quantum networks operating in research labs, e.g., between universities in a city. Teleportation with independent sources demonstrated, Stuttgart breakthrough. 2025 to 2030, near term. First metropolitan-scale quantum networks deployed in major cities. Quantum repeaters demonstrated over longer distances. Integration of quantum networks with classical internet infrastructure. Commercial applications in finance and government communication. 2030 to 2040, mid-term. Continental-scale quantum networks linking cities across countries. Distributed quantum computing between networked quantum computers. Quantum-enhanced GPS and timing systems operational. Quantum internet becomes a recognized infrastructure layer. 2040 to 2050, long-term. Global quantum internet spanning continents via satellite and undersea cables. Routine use of quantum communication for secure transactions. Quantum sensors networked for scientific research, e.g., gravitational wave detection. Quantum internet integrated into daily life, invisible but essential. This timeline is speculative, but the trajectory is clear. The November 2025 Stuttgart breakthrough removes a major bottleneck, proving that independent source teleportation works. The path to a quantum internet is now technically feasible, with challenges being engineering and scale, not fundamental physics. As you close your eyes tonight, imagine a future where information flows not just through copper wires and fiber optics, but through entangled photons, teleporting across the globe. A network where security is absolute, where quantum computers collaborate across continents, where sensors entangled across space detect the faint ripples of gravitational waves or the whisper of dark matter. This future is being built now, in laboratories in Stuttgart, Vienna, Beijing, and Boston. The quantum internet is coming, and quantum teleportation is its foundation. In the next chapter, we'll confront the limitations, what teleportation cannot do, the misconceptions to avoid, and why Star Trek's transporter remains firmly in the realm of fiction. Chapter 6. What teleportation cannot do, the limits of the possible. Quantum teleportation is remarkable, but it's not magic. Let's be clear about what it can and cannot do, separating fact from fantasy. You cannot teleport matter. Quantum teleportation transfers quantum information, not physical objects. When you teleport the state of a photon, the photon itself, the particle of light, doesn't move. You're teleporting the abstract information describing its quantum state, its polarization, its phase, its superposition. The photon at the destination isn't the same photon as the one at the source. It's a different photon, reconfigured to have the same quantum state. For teleporting a person, a la Star Trek, you'd need to scan every particle in their body, roughly 10 to the 28th atoms, record their quantum states, transmit that information, and reconstruct them at the destination. This faces insurmountable obstacles. 1. The uncertainty principle. You cannot measure both position and momentum precisely, so perfect scanning is impossible. 2. The sheer information. A human body contains about 10 to the 45th bits of classical information, approximating quantum states. Transmitting this would take longer than the age of the universe using any conceivable technology. 3. The no-cloning theorem. You'd have to destroy the original to avoid creating a copy, which raises existential questions. So no, we're not teleporting people. Quantum teleportation is for quantum information, qubits, photon states, quantum computer data. You cannot send information faster than light. This is a common misconception. Doesn't entanglement allow instant communication? No, here's why. When Alice performs her Bell state measurement, photon C, held by Eve, undergoes a transformation instantly. But Eve cannot determine what transformation occurred without Alice's classical message. Eve receives a randomized version of the original state. It looks like noise. Only after Alice sends her measurement result, traveling at light speed, can Eve decode it. If Alice never sends the message, Eve has nothing useful. The quantum state alone conveys no information until the classical message arrives. Quantum teleportation respects causality. No signals travel faster than light. Relativity remains intact. You cannot clone quantum states. The no-cloning theorem states you cannot create an identical copy of an unknown quantum state. Teleportation doesn't violate this because the original state is destroyed. If you try to teleport and keep the original, the mathematics doesn't work. The measurement collapses the original state, erasing it. Teleportation is transfer, not duplication. This has practical implications. You can't use teleportation to copy a quantum computer's memory or duplicate a qubit for backup. Once you teleport, the original is gone. Teleportation requires pre-shared entanglement. You can't teleport without entanglement already in place. Alice and Eve need to share entangled photons before teleportation begins. Creating and distributing this entanglement takes time and resources. For a quantum internet, this means establishing entanglement links across the network ahead of time, a logistical challenge. Moreover, entanglement is fragile. Photons can be lost, states can decohere. Maintaining a network of fresh entanglement is a continuous effort. Fidelity is never perfect. Real-world teleportation is imperfect. Noise, detector inefficiencies, timing errors all reduce fidelity. The Stuttgart team achieved 85% fidelity, meaning 85% overlap between the teleported state and the original. That's excellent. Well above the classical limit, but not perfect. For practical quantum communication, you want fidelities above 99%. Achieving this requires better sources, better detectors, better control, ongoing areas of research. Teleportation is probabilistic. Bell state measurements don't always succeed. Detectors might not click, photons might be lost, interference might fail. In many experiments, the success rate is low. Only a few % of attempted teleportation succeed. This is acceptable for demonstrations, but problematic for applications. Improving success rates requires better photon collection, more efficient detectors, and error correction. Quantum repeaters will help, but we're not there yet. Energy and matter are not teleported. Science fiction often conflates teleportation with transmutation, converting matter into energy, beaming it, and reconstructing it. This is unrelated to quantum teleportation. Quantum teleportation doesn't involve energy beams or matter streams. It's a protocol for transferring quantum states using entanglement and classical communication. The physics is subtle, not dramatic. Why these limitations matter. Understanding what teleportation cannot do helps us appreciate what it can do. Quantum teleportation enables secure communication via QKD, distributed quantum computing, networking quantum sensors, extending the range of quantum information transfer. These applications are transformative, even if they're not as flashy as Star Trek. And here's the deeper point. Science doesn't need to replicate fiction to be wondrous. The real universe is stranger and more interesting than any invented story. Quantum teleportation is real. It works. It's being used and refined. The fact that it doesn't transport people doesn't diminish its significance. It amplifies it, because it shows that reality, explored carefully and deeply, offers marvels beyond imagination. As you drift toward rest, consider this. Every technological breakthrough faces limitations. Airplanes can't fly at light speed. Computers can't think like humans yet. Quantum teleportation can't transport matter, but within their domains, these technologies are revolutionary. The quantum internet will reshape communication, computation, and science, even if it doesn't let us beam to distant planets. Progress is about expanding the possible, not fulfilling every fantasy. And the November 2025 Stuttgart breakthrough expanded the possible significantly. In the next chapter, we'll explore competing approaches to quantum networking, alternative methods for distributing entanglement and transmitting quantum information. Chapter 7: Alternatives and Competitors, the Quantum Networking Landscape. Quantum teleportation is one tool in the quantum networking toolkit, but it's not the only approach. Let's survey the broader landscape of how quantum information can be transmitted and entanglement distributed. Direct transmission. The simplest method: just send the quantum state directly. Encode information in a photon's polarization, launch it down a fiber optic cable, and detect it at the destination. This works for short distances, tens to hundreds of kilometers, but photon loss limits range. After 500 kilometers in fiber, almost no photons remain. Free space transmission through air or vacuum is better. The Chinese Mir satellite demonstrated quantum communication over thousands of kilometers using this approach. But direct transmission has vulnerabilities. Photons can be intercepted, measured, disrupted. For secure communication, you need quantum key distribution protocols to detect eavesdropping. Teleportation, by contrast, uses entanglement to transfer states without the state existing in the channel. This makes interception harder, though not impossible. Eve could attack the entanglement distribution phase. Quantum repeaters. We've mentioned these already, but let's go deeper. A quantum repeater divides a long-distance link into segments, establishes entanglement across each segment, and uses swapping to connect them. This overcomes photon loss because each segment is short enough that loss is manageable. The challenge is building reliable quantum memories to store photons while swapping occurs. Several technologies are being explored. Rare earth-doped crystals. Materials like erbium-doped yttrium, orthosilicate can store photons for milliseconds to seconds. Atomic ensembles. Clouds of cold atoms can store quantum states collectively. Nitrogen vacancy centers in diamond. Defects in diamond's crystal structure can trap photons and store their states. Each has trade-offs. Rare earth crystals operate at cryogenic temperatures. Atomic ensembles are delicate. Nitrogen vacancy centers have limited storage times, but progress is rapid. In 2023, a team at Harvard demonstrated a quantum memory with storage times exceeding 1 second, a record. With such memories, quantum repeaters become practical. Photons travel through space with minimal loss, making satellites ideal for long-distance quantum communication. The Michius satellite, launched by China in 2016, demonstrated QKD between Beijing and Vienna, separated by 7,600 kilometers. It also performed quantum teleportation from ground to space. Future satellite constellations could create a global quantum network, with ground stations distributing entanglement locally and satellites linking continents. Companies like SpaceX and Amazon are launching vast constellations of classical communication satellites. A quantum satellite network could follow a similar model, blanketing the Earth with quantum links. Most quantum networking uses photons, but you can also use atoms, ions, or solid-state qubits. Trapped ion systems, for example, can store quantum states for hours and perform high-fidelity gates. Linking trapped ions with photons creates a hybrid network. Ions for quantum memory and computation, photons for transmission. In 2020, researchers at MIT and Harvard demonstrated entanglement between a trapped ion and a photon separated by fiber optic cable. This is a building block for ion-photon quantum networks. Similarly, superconducting qubits, used in Google and IBM quantum computers, can be interfaced with photons through microwave to optical conversion, enabling networks of superconducting quantum processors. Continuous variable quantum communication. Most quantum networking uses discrete variables, individual photons, qubits in zero-angle bracket or one-angle bracket. But there's an alternative, continuous variable quantum communication, which encodes information in the amplitude and phase of light fields. This approach uses different mathematical tools, Gaussian states, homodyne detection, and has advantages for certain applications like quantum-enhanced sensing and secure communication with standard telecom equipment. Continuous variable teleportation has been demonstrated, though it's less common than discrete variable teleportation. For a quantum internet to work, different systems must interoperate. Photons from a quantum dot source in Stuttgart should be compatible with detectors in Vienna, repeaters in Geneva, and quantum computers in Amsterdam. This requires standards, agreed upon protocols, wavelengths, timing, error correction codes. Organizations like the Quantum Internet Alliance, Europe, and the Quantum Economic Development Consortium, US, are working on these standards, bringing together universities, companies, and governments. International collaboration is also crucial. Quantum networks will span borders. The Michius satellite, for example, was a collaboration between China, Austria, and other countries. The November 2025 breakthrough in context. The Stuttgart independent source teleportation fits into this broader landscape as a key enabling technology. It proves that quantum networks can be modular, with nodes operating independently. This is essential for scaling. You can't build a global quantum internet if every node needs to share a common source. Other approaches, satellite networks, quantum repeaters, continuous variable systems, complement teleportation. A mature quantum internet will likely use all of them, choosing the best tool for each link. As you rest tonight, picture this ecosystem. Photons traveling through fiber and space, atoms storing quantum states in laboratories, satellites orbiting overhead, all connected by protocols and standards, forming a global web of entanglement. No single technology dominates. Progress comes from diversity, from exploring every possibility, from competition and collaboration. The quantum internet will be a mosaic, built from many pieces, each essential. In the next chapter, we'll explore the future. What comes after the November 2025 breakthrough, and where quantum teleportation might lead us in the decades ahead. Chapter 8. The future of teleportation. Where do we go from here? The November 2025 Stuttgart breakthrough is a beginning, not an end. What comes next? Where will quantum teleportation take us? Let's explore the horizons. Near term 2025 to 2030. Metropolitan quantum networks. The first practical quantum networks will likely be metropolitan, linking universities, research labs and businesses within a city. Imagine a quantum network in Boston, connecting MIT, Harvard, Boston University, and quantum computing startups. Researchers could share entanglement, run distributed quantum algorithms, and test new protocols. Similar networks are being built in Vienna, Beijing, Tokyo, and other cities. The Stuttgart breakthrough accelerates this by enabling independent nodes to join seamlessly. By 2030, dozens of cities might have operational quantum networks, creating a testbed for applications and a proving ground for technologies. Mid-term 2030 to 2040, continental networks. The next step is linking cities across countries. In Europe, the Quantum Internet Alliance aims to connect quantum networks in multiple countries by 2035. Fiber optic cables would span the continent, with quantum repeaters at intervals to combat photon loss. In the US, the Department of Energy's National Quantum Initiative includes plans for a quantum internet linking national laboratories and universities. China is already building a quantum communication backbone, extending thousands of kilometers. By 2040, continental-scale quantum networks could be operational, enabling applications like distributed quantum computing clusters, solving problems beyond the reach of any single machine. Long-term, 2040 to 2050, the global quantum internet. The ultimate vision, a globe-spanning quantum network, linking continents via satellites and undersea cables. This would require significant advances. Space-based quantum repeaters. Satellites that perform entanglement swapping, extending quantum links across oceans. High-rate quantum sources. Photon sources producing millions or billions of entangled pairs per second. Efficient quantum memories. Storage times of minutes to hours, allowing long-distance swapping. Integrated photonics. Miniaturized quantum devices on chips, reducing cost and complexity. All of these are active research areas, with progress reported regularly. A global quantum internet would transform cybersecurity. Unbreakable encryption for governments, militaries, banks. Scientific collaboration. Quantum sensors worldwide entangled for synchronized measurements, enabling discoveries in fundamental physics. Distributed AI, quantum machine learning algorithms running across networked quantum computers. Wild speculations, quantum communication beyond Earth. Could we teleport quantum states to the Moon, to Mars, to distant star systems? For the Moon, it's plausible. The distance is 384,000 kilometers, within range of satellite-based quantum communication. A lunar quantum network could support future bases, enabling secure communication and networked quantum sensors for astronomy. Mars is harder. The distance varies from 55 million to 400 million kilometers. Photon loss over such distances is enormous. Even with quantum repeaters, the challenges are formidable. But if we establish colonies on Mars, building a local quantum network there is feasible. Communication with Earth might rely on classical channels, but Mars-based quantum networks could support local quantum computing and sensing. For interstellar distances, light years, quantum communication as we understand it breaks down. Photon loss, time delays, and cosmic radiation make it impractical. But here's a speculative thought. If we ever develop faster than light travel or communication, purely hypothetical, quantum entanglement might play a role. Imagine pre-shared entanglement between Earth and a distant spacecraft. Teleportation could transfer quantum states across light years, using entanglement created before departure. This is far beyond current physics, venturing into the realm of science fiction. But entanglement's non-locality hints that space and time are more flexible than we intuitively grasp. Fundamental physics, what teleportation teaches us. Beyond applications, quantum teleportation probes deep questions about reality. If quantum states can be transferred without traversing space, what does that imply about the nature of information? Is information more fundamental than matter or energy? Physicist John Wheeler famously proposed it from bit, the idea that physical reality emerges from information. Quantum teleportation supports this view, showing that what we perceive as things are really patterns of information, and those patterns can move in ways that defy classical intuition. Teleportation also illuminates the relationship between quantum mechanics and relativity. Both theories are central to modern physics, yet they're famously difficult to reconcile. Teleportation respects both. It uses entanglement, quantum, while preserving causality, relativistic. Studying how teleportation navigates this boundary might offer clues toward a unified theory. The ethics of quantum communication. As quantum networks grow, ethical questions arise. Privacy. Quantum communication is provably secure, but who controls the networks? Governments might mandate backdoors, but quantum mechanics makes this difficult. How do we balance security and oversight? Equity. Quantum technologies are expensive. Will quantum internet access be a luxury for wealthy nations and corporations, or will it be made universally accessible? Dual use. Quantum communication can protect both legitimate users and criminals. How do we prevent misuse without undermining the technology's benefits? These questions have no easy answers, but they'll shape how quantum networks are deployed and regulated. Amid the physics and engineering, let's not forget the human story. The researchers building quantum networks, people like Harold Weinfurter, Anton Zeilinger, Jianwei Pan, and thousands of others, are driven by curiosity, by the desire to understand and build, by the thrill of discovery. They work in labs, often late at night, troubleshooting equipment, analyzing data, refining techniques. They collaborate across borders, share knowledge, compete, and cooperate. The November 2025 breakthrough is their achievement. Years of effort, setbacks, perseverance, and ultimately success. And it's also our achievement collectively. Society funds this research through universities and grants. The knowledge belongs to all of us. As quantum teleportation moves from labs to applications, it will touch our lives in ways we can't fully predict. Perhaps one day, your smartphone will use quantum-secured communication. Perhaps your doctor will use quantum-enhanced MRI guided by networked sensors. Perhaps your children will take quantum internet access for granted, the way you do classical internet today. The future is being built now, one entangled photon at a time. As you close your eyes and drift, imagine the tapestry of possibility. Researchers in labs, satellites orbiting, photons entangling across continents, information teleporting through networks, all contributing to a future where the quantum realm is not mysterious but mundane, not exotic but essential. This is the legacy of November 2025, proof that the dream is real and the journey has just begun. In the final chapter, we'll reflect on what all this means for science, for humanity, and for our place in a quantum universe. Chapter 9: Quantum Teleportation and the Nature of Reality. We've explored the physics, the experiments, the applications. Now let's step back and ask, what does quantum teleportation reveal about the nature of reality itself? This question takes us into philosophy, into the deepest mysteries of quantum mechanics, into the territory where science and wonder merge. Information as fundamental. Quantum teleportation suggests that information is more fundamental than matter. When you teleport a photon state, the photon itself doesn't move. The matter, the physical particle, stays put. What moves is the pattern, the information, the abstract description of the state. Yet that information is enough to recreate the state perfectly at a distant location. The information is the essence. The particle is just a substrate. This aligns with a view growing in physics, that the universe is fundamentally informational. Matter and energy are manifestations of information, patterns in the quantum field, shapes in Hilbert space. If so, then teleportation is revealing a deep truth, that what we think of as things are really information structures, and those structures can be transferred, manipulated, stored, and processed in ways that transcend physical boundaries, entanglement and non-locality. Teleportation relies on entanglement, and entanglement is non-local. It correlates events across space in ways that cannot be explained by any local hidden variable theory. Einstein resisted this, believing that reality must be local, that influences propagate through space at finite speeds, that distant events are independent until light speed signals connect them. But experiments have vindicated quantum mechanics. Entanglement is real. The universe is non-local. What does this mean? It means space is not a fundamental separator. At the quantum level, distance is negotiable. Particles can be correlated in ways that defy spatial separation. Some physicists interpret this as evidence that space itself is emergent, not fundamental. Perhaps the universe, at its deepest level, is a network of quantum correlations, and space is just the pattern those correlations create, an illusion, like the surface of a hologram. Teleportation taps into this deeper layer, moving information through channels that don't correspond to paths through space. Here's a poetic way to think about it. The universe is a vast quantum state, a superposition of all possible configurations. What we perceive as now is a slice through that state, a particular configuration selected by observation. Entanglement weaves connections through the quantum state, linking distant parts. Teleportation uses those connections to transfer patterns, to move information from one part of the state to another without the information passing through the intermediate slices. It's like editing a document on a computer. You delete a paragraph here, paste it there. The text doesn't travel through the screen. It moves through the computer's memory, through abstract data structures. Space, in this analogy, is the screen, what you see. But reality operates in the memory, where connections are more flexible. Consciousness and observation. Does consciousness play a role in teleportation? Some interpretations of quantum mechanics, like the von Neumann-Wigner interpretation, suggest that conscious observation causes wave function collapse, turning quantum superpositions into definite outcomes. In teleportation, the Bell state measurement collapses the superposition, projecting the system into one of four states. Is this collapse due to the measuring device, or does it require a conscious observer to see the result? Most physicists today favor the decoherence interpretation, where interaction with the environment, not consciousness, causes apparent collapse. The measuring device becomes entangled with the measured system, and the macroscopic device's state becomes correlated with the outcome, creating the appearance of collapse without invoking consciousness. But the question isn't fully settled. Some researchers, like Matthew Fisher, UC Santa Barbara, explore whether quantum processes in the brain, protected from decoherence, might play a role in cognition or consciousness. If so, then human observers performing Bell state measurements might be engaging in a quantum process that connects consciousness and information transfer in subtle ways. This is speculative, verging on philosophy, but it's a reminder that quantum mechanics still harbors mysteries, and teleportation sits at the intersection of those mysteries. The unreasonable effectiveness of mathematics. Physicist Eugene Wigner famously wrote about the unreasonable effectiveness of mathematics in the natural sciences. Why does math describe reality so well? Quantum teleportation is a prime example. The protocol was derived mathematically from abstract algebra and Hilbert spaces before anyone knew if it would work physically. Yet, it does work. The math predicted it, and nature obeyed. This suggests that mathematics is not just a tool we invented, but a language in which the universe is written. Quantum states are vectors, measurements are operators, probabilities are born rule calculations. The universe computes, using quantum mechanics as its algorithm. Teleportation shows this vividly. You can predict, using equations, that performing certain operations on photons will transfer states across space, and when you build the apparatus and try, it happens, exactly as the math said it would. The universe, it seems, is mathematical. Or perhaps we are quantum systems ourselves, and our brains have evolved to think in ways that mirror the quantum substrate, making math feel natural because it reflects the structure we're made of. Finally, there's something poetic, almost spiritual, in the idea of entanglement and teleportation. We often think of the universe as vast, empty, isolating. Distances separate us. Space is cold, indifferent. But entanglement reveals a different truth. The universe is intimately connected. Particles across the cosmos can be correlated. Information can be shared without transmission. What happens here can be instantly reflected there, not through force or signal, but through the deeper fabric of quantum reality. Teleportation is a technology, yes, but it's also a reminder that separateness is an illusion. At the quantum level, we're all woven together, part of a single, interconnected whole. This doesn't imply mysticism or magic. It's physics, grounded in equations and experiments. But it does invite us to see the universe differently, as less fragmented, more unified, more alive with invisible threads linking every part. As you drift towards sleep, imagine yourself as part of this web. Atoms in your body forged in ancient stars, photons streaming from the sun, quantum states entangled across space and time. You are not separate from the universe, you are the universe, experiencing itself. And quantum teleportation, in its strange and beautiful way, makes this connection tangible, demonstrating that information, perhaps the essence of what you are, can move through channels invisible, eternal, and profound. In the final chapter, we'll close with reflections on what the November 2025 breakthrough means for the future, for science, and for the human journey. Chapter 10. The Journey Continues. Reflections on Impossibility and Wonder. We've travelled far tonight, from Captain Kirk's transporter to the Stuttgart laboratory, from Einstein's skepticism to Zeilinger's experiments, from the mathematics of Bell states to the philosophy of information. Let's pause and reflect on what the November 2025 breakthrough means. From science fiction to science fact. In 1966, Star Trek premiered, introducing the transporter. It was a budget-saving plot device, cheaper to beam actors than build shuttle landing sets, but it captured imaginations. Could we ever do that? Could we teleport? For decades, the answer seemed to be no. Physics forbade it. Uncertainty, no cloning, causality, all stood in the way. But then, in 1993, physicists asked a different question. What if we teleport not matter, but quantum information? And the answer was, yes, that's possible. In 1997, it was demonstrated. In 2025, it became practical. This is the pattern of science. What seems impossible becomes possible when we ask the right questions, explore the right theories, and build the right technologies. The impossible shrinks as knowledge grows. Heavier-than-air flight was impossible until the Wright brothers. Splitting the atom was impossible until Fermi. Reaching the moon was impossible until Apollo. Quantum teleportation joins this legacy. Not the teleportation of people, but something just as profound. The transfer of quantum information across space, using the deepest principles of quantum mechanics. Science fiction inspired it. Science made it real. The November 2025 breakthrough wasn't driven by commercial need or military urgency. It was driven by curiosity, the desire to understand, to explore, to see if something is possible. Harold Weinfurter and his team didn't build their apparatus because someone paid them to. They built it because they wondered, can we teleport between independent sources? Anton Zeilinger, decades earlier, didn't pursue teleportation for profit. He did it because Bennett's paper fascinated him, and he wanted to see if it worked. Charles Bennett didn't invent quantum teleportation to get rich. He did it because the mathematics intrigued him. This is fundamental research. Exploration without guaranteed applications, driven by the intrinsic joy of discovery. And yet, from this curiosity, applications emerge. Quantum networks, secure communication, distributed computing, all made possible by research that began with wonder. This is why we fund science, not just for immediate utility, but for the long-term harvest of knowledge, for the technologies that bloom from seeds planted by curious minds. Quantum teleportation's history spans continents, decades, and thousands of researchers. Einstein's EPR paradox in 1935, Bell's theorem in 1964, Bennett's protocol in 1993, Zeelinger's demonstration in 1997, the Chinese satellite in 2017, the Stuttgart breakthrough in 2025. Each step required many people, experimentalists, theorists, engineers, technicians, students. Some are famous, most are not, but all contributed. Science is collaborative, cumulative, built by communities working across borders and generations. The November 2025 result is humanity's achievement, not an individual's, and it's available to all. The knowledge is published, open, shared. Anyone can read the Stuttgart paper, understand the methods, and build on them. This openness is science's strength. Ideas spread, replicate, improve. No one owns the truth. We discover it together. Where will quantum teleportation lead? We can imagine quantum networks, secure communication, distributed computing. But the most transformative impacts are often unpredictable. When the internet was being built in the 1960s and 70s, few imagined social media, streaming video, or global e-commerce. The applications emerged as the technology matured. Similarly, quantum networks will enable applications we haven't conceived yet. Perhaps quantum-enhanced virtual reality, where entangled states create perfectly synchronized, immersive experiences. Perhaps quantum-assisted medical diagnostics, where networked sensors detect diseases with unprecedented sensitivity. Perhaps entirely new forms of art, communication, or expression built on quantum principles. The future is uncertain, but it's full of possibility, and the November 2025 breakthrough expands that possibility space, opening doors we didn't know existed. Ultimately, quantum teleportation is part of a larger story, humanity's quest to understand and shape the world. For millennia, we've explored. Geographically, intellectually, technologically, we've ventured across oceans, into space, and now into the quantum realm. Each exploration changes us. The telescope revealed the vastness of the cosmos, humbling our sense of place. The microscope revealed the complexity of life, deepening our reverence for nature. Quantum mechanics reveal the strangeness at reality's core, challenging our intuitions and expanding our minds. Quantum teleportation is part of this journey, a step deeper into the strange, a glimpse of principles that govern the universe, a tool to build futures we dream of, and it reminds us that the universe is more wonderful than we ever imagined, more connected, more mysterious, more rich with potential. We are explorers, traveling not just through space but through knowledge, each generation building on the last, each discovery illuminating the path ahead. As you rest tonight, consider this. Somewhere in Stuttgart, a laboratory stands quiet. Lasers are powered down, detectors idle, optical tables still, but the knowledge created there lives on. It's in papers published, in ideas shared, in students taught, in technologies being built. It's in the quantum internet slowly taking shape, in the entangled photons linking cities, in the future being woven from light and information. The November 2025 breakthrough is a moment, a milestone on a journey that began with Einstein's discomfort and continues with every photon teleported, every state transferred, every question asked. And you, listening to this, are part of that journey. By seeking to understand, by embracing curiosity, by wondering at the strangeness and beauty of the quantum world, you participate in the collective exploration. Science is not something distant, done by others. It's a human endeavor, open to all who wonder, who ask, who seek. Quantum teleportation is real, it's becoming practical, and it's a testament to what we can achieve when we follow curiosity, embrace complexity, and dare to ask, what if the impossible is just the not yet possible? May your dreams be filled with entangled states, with photons dancing through fiber, with information teleporting across space, with the wonder of a universe that never ceases to surprise. And so we arrive at the end of this quantum journey, from science fiction to science fact, from Einstein's doubts to Stuttgart's triumph. If this exploration stirred something within you, a sense of wonder, a spark of curiosity, or simply a quiet appreciation for how far humanity has come, I invite you to subscribe to Sleep Entangled. Like this video to share the marvel of quantum teleportation with others seeking understanding, and comment, what aspect of teleportation fascinates you most? This is Sleep Entangled, where quantum breakthroughs and contemplative wonder merge into meaning. Until we meet again beneath the stars, rest peacefully knowing that the universe is stranger, more connected and more wonderful than any fiction could imagine. Beam me up? Not quite. But teleport information across space using quantum entanglement. That we can do. The quantum future is here.